Welcome to my podcast, Scientist Free from Religion. This podcast has as proposal, as main idea to talk about a scientific topic, but also talk about religion. Different from the common assumption in which science and religion should be separated, here on this podcast we recognize formally that science and religion are not disconnected. Sadly, religion can be a very big threat to science. So on this podcast, the proposal is to talk about it freely, so without fear, without the illusion that they are separate topics. So we are going to cover a possible topic. Most of them will be focused on the connection between religion and science, especially to defend science. That's our goal. Our goal here is to defend science from religion and to help to make science, to spread scientific thinking, especially to defend it against religion.
Okay, let's unpack this. Welcome back to the deep dive. Today, we are wading directly into what's probably the most sophisticated argument, maybe the most intimidating one, that links cosmology to, well, the need for a creator.
Yeah.
We are confronting the fine-tuning argument.
Yeah, it's a big one.
It really is. And this claim is powerful because it actually uses real physics, right? It focuses on this idea that the universe's fundamental properties, the constants, the laws, they seem so perfectly set up for life, like exquisitely tuned.
Right. And the implication, the argument goes, is that this precision, it just can't be an accident. It seems to demand some kind of deliberate intelligence behind it all.
Exactly. So our mission today is to really hold the scientific critique up against that philosophical assertion. We're going deep into the established, the predictive power of the big models in physics, the standard model for particles and forces, and the standard model of cosmology.
The concordance model, yeah. Lambda CDM.
Right, lambda CDM. And we want to see if this alleged fine-tuning is really fine-tuning, or maybe just a coincidence, or perhaps even, well, a mathematical necessity. Something that has to be that way.
That's the core question, isn't it? Is it choice or is it necessity? Do these precise values, these constants, do they really require what some proponents call a super-calculating designer?
Mm-hmm.
Or can the constraints, the symmetries that are just inherent in natural law, can they explain these values without needing, an external tuner?
That distinction, choice versus necessity, that feels like the absolute hinge point for this whole deep dive.
It really is. But first, we should probably give the argument its due. I mean, life does depend incredibly sensitively on these parameters. That part's true.
Oh, absolutely. You change gravity just a tiny bit.
And stars burn out too fast, or maybe they never ignite properly, or change the electron's mass, and suddenly all of chemistry as we know it just vanishes. Oof.
Right. So the sensitivity is real.
The sensitivity is definitely real. But the leap, the conclusion that this sensitivity requires an external, intentional fine-tuning, a creator entity sort of operating outside the universe, that's where we need to apply the scientific lens rigorously.
And to understand why this argument has so much, well, rhetorical weight, you have to appreciate the kind of numbers involved, the scale of improbability they talk about.
Exactly. You hear people like William Lane Craig asserting that universes that don't allow life are just vastly more probable than one like ours.
And here's where it gets really, really interesting, because the numbers they quote are just mind-bending. When people talk fine-tuning, they often bring up estimates from giants like Roger Penrose.
Right, about the early universe's entropy state.
Yeah, he estimated the probability of our specific universe with its low entropy start existing randomly, 1 in 10 to the power of 10 to the power of 123?
That's the one, 10, 10, 10. It's a number so vast, it's basically meaningless in practical terms.
Yeah.
You couldn't even write down the zeros.
And theological advocates, like you see with Michael Anthony Corey, they grab onto that figure. They use it to talk about a miraculous level of microengineering.
They do. And look, right at the start, we need to be really clear with you, the listener. Is that staggering improbability a genuine reflection of design? Or is it maybe just an artifact, something that comes out of a calculation or an assumption that's fundamentally flawed? Science, as we'll see, makes a pretty strong case for the latter. That the number, while mathematically derived from certain assumptions, doesn't actually represent the odds of this universe existing naturally.
Okay, so before we start dismantling specific constants, let's maybe nail down the definitions that frame this whole debate, specifically those anthropic principles. Brandon Carteret, 1974.
That's right. Carter introduced them.
So first up, there's the weak anthropic principle, WAAP.
This one seems, well, Pretty straightforward.
It is. It's the simplest, least controversial. Basically, it just states that our location in the universe, both in space and time, has to be compatible with us being here to observe it. So it's kind of obvious, like, if the laws weren't right for life, we wouldn't be here discussing them.
Pretty much. It's often described as tautological for that reason. Think about it simply. If gravity were totally different, no galaxies. No galaxies, no stars, no heavy elements made inside them.
No carbon, no oxygen, no us.
Exactly. So the mere fact that we exist automatically places us in a part of the universe and at a time in its history where the conditions are right for observers to evolve. It's a selection effect.
Okay, makes sense.
Mm-hmm.
But then there's the strong anthropic principle, the SAP.
Mm-hmm.
And this one feels like it carries a lot more philosophical weight.
It definitely does. The SAP states that the universe must have properties that allow life to develop within it at some point in its history. It shifts from just we observe it this way because we're here to it had to be this way for life to eventually arise.
So it implies some kind of necessity, almost a purpose,
Mm-hmm.
for the universe to be life-generating.
That's the implication, yeah. And it's a much stronger, more controversial claim. And, while we're at it, we can't forget the humorous additions.
Oh, right, the FAP.
The final anthropic principle, yes.
Right.
Which Martin Gardner jokingly called CRIP the completely ridiculous anthropic principle.
What did that one say again?
It basically posited that once intelligent life like us arises, it will eventually process all the information in the universe and become effectively immortal or something.
Oh, definitely sliding into metaphysics there.
Yeah, Gardner used it to show how easy it is to slip from, serious physics into pretty wild speculation.
Right. So once proponents feel they've established the SAP, or at least the incredible improbability arguments, they often feel they can jump straight to theological conclusions. And these aren't fringe arguments, are they? They pop up in serious discourse.
Not at all. You see respected figures making these claims. Edward Robert Harrison saying fine-tuning gives prima facie evidence at first glance of deistic design.
And Francis Collins, a geneticist, arguing the precise tuning isn't an accident, but reflects the action of the one who created the universe.
Mm-hmm. And it connects to older ideas, too. I like that Tony Rothman quote suggesting the modern cosmologist doesn't see God's hand in angels anymore, but
in the constants of nature,
yeah,
the constants become the divine fingerprints.
Exactly. So that really sets the stage for the scientific counterargument. How does science actually push back against these powerful, almost emotionally resonant claims based on these huge numbers?
Right. What's the methodology?
Well, science has to rely on its core tools, models, and falsification. We observe things, we collect data, and we describe that data using mathematical models.
Okay.
But a model only really becomes a theory in the strong scientific sense if it passes what Karl Popper called risky tests. It has to make predictions that are specific enough that they could actually be proven wrong.
If a model can explain anything, it explains nothing.
Precisely. If it can't be falsified, it's not really science. Now, science is always tentative, right? We're always open to new data, better models. But when models like general relativity or quantum mechanics pass decades, even a century, of really tough, risky tests,
the confidence level gets incredibly high.
Yeah, it approaches certainty for all practical purposes. We can say, scientifically, that a flat Earth or a 6,000-year-old universe is just wrong, beyond a reasonable doubt, as the source material puts it.
So if the fine-tuning argument relies on probability, it's just too unlikely? The scientific refutation needs to rely on necessity, on showing why these constants had to be the way they are.
Exactly. And this is where we introduce the really crucial physics principle that underlies a lot of the refutation, point of view invariance, which is fundamentally about symmetry.
Symmetry. Okay. And this connects to Emmy Noether.
The brilliant mathematician Emmy Noether, yes. Back in 1915, she proved this incredible theorem.
What did it show?
Noether's theorem proved that for every continuous, differentiable symmetry you find in the laws of nature, there exists a corresponding conserved quantity. A conservation law.
Okay, break that down. What does symmetry mean here and conservation law?
Hey there, thanks for being around. We are going to make a small break. I'm going to share with you my books. I have several books. So far, all my books about religion, atheism, which have been published a lot, they are in Portuguese, which is my main focus. But if you are interested, you can still buy my books to help me to support my work. I have several books. For example, one book that I'd like to recommend now is AI by Sci-Fi. AI by Sci-Fi is a book that talks about artificial intelligence, which is everyone is talking about artificial intelligence with ChatGPT, all this amazing stuff that they can do. They can talk, they can create video, they can create podcasts. This podcast, for example, there are several episodes that was recorded using artificial intelligence, which is amazing how I can do that. I can even interact as you could see in several episodes. So I would like to invite you to buy my book AI by Sci-Fi. It's available on Google Books, Google Play. It's also available on Amazon. So you can buy my book. If you are interested in something a little bit more complex, a little bit more technical, I do have as well technical book. For example, I have one book about computational thinking, in which I talk about Kasparov. It's a technical book. Greg Kasparov was the first guy to be beaten by a computer. He has a very nice book about that, how artificial intelligence overturned the difference between human and artificial intelligence. So please buy my book and offer me all the support. You can find all of them on Amazon. Hopefully, in the future, I'm going to write also about religion, atheism, and science. But I do have a podcast. I do have a blog called the Scientists Free from Religion. The same name of the podcast. And you can find several already publications about several topics in which talk about science, religion, and atheism. So, hope you enjoyed the show. So, let's come back to the show.
So symmetry means the physics looks the same regardless of your perspective. For example, if the laws of physics work the same way today as they did yesterday, that's symmetry under time translation.
Wow.
And Noether showed that because of that time symmetry, energy must be conserved. The total amount of energy in a closed system stays constant.
Wow. So energy conservation isn't just some rule someone made up.
Nope. It's a direct mathematical consequence of the laws being the same over time. Same goes for momentum. The laws work the same if you do your experiment here, or 10 feet to the left, that's symmetry under spatial translation.
And that leads to
Conservation of linear momentum. And symmetry under rotation, the laws don't care which way you're facing, leads to conservation of angular momentum.
So these fundamental conservation laws, energy, momentum, they aren't arbitrary rules that a creator needed to build into the universe.
Exactly. They are automatic required consequences of building an objective physical model. A model that works no matter who is observing or where or when. These principles govern how we must describe nature if we want our description to be objective.
That flips the script entirely. Yeah. It's about the rules of model building, not rules handed down.
Precisely. And this concept of necessity, driven by symmetry and invariance rather than arbitrary choice, that's the tool we're going to use to dissect this idea of fine-tuning constant by constant.
All right. With that framework necessity from invariance, let's tackle maybe the easiest targets first, the constants that seem arbitrary just because of how we define things.
Yeah, the low-hanging fruit. It seems weird to think that quantities that are basically human inventions, artifacts of how we choose to measure things, would need some external cosmic force to set their specific numerical value.
Oh, the speed of light, CT, that's always mentioned.
Right. C is a classic example. It's often cited as this crucial, finely tuned value. But what is the speed of light today, officially?
It's 299,792,458 meters per second.
Exactly. 299,792,458. Why? Because since 1983, the meter itself is defined as the distance light travels in a vacuum in exactly 299,792,458 of a second.
Ah, so it's fixed by definition. If I measure C, I get that number because I define my ruler, my meter stick, using that very number.
Precisely. It's a human convention. So if someone writes that C is fine-tuned for life, well, they're basically ignoring the internationally agreed-upon definition of distance and time that we use in science.
The actual number in meters per second doesn't have some deep physical significance.
Not really. As the source says, its value has no fundamental role in physics. In theoretical physics, especially when using Planck units, we often just set C equals 1. It simplifies the equations and shows the underlying physics doesn't depend on that specific meters per second number.
Okay, so C is out. What about others, like Planck's constant h or Newton's gravitational constant g?
Same basic issue. Their numerical values depend entirely on the units we choose. What units do we use for mass? Kilograms? Pounds? Something else. Change the mass unit and the number for g changes.
Change the time unit, h changes.
Exactly. So the only parameters that are really legitimate candidates for fine-tuning discussions are the ones that are dimensionless, ratios of physical quantities where the units cancel out. These numbers are the same no matter what system of measurement you use.
That makes sense. The relationships between things matter, not the arbitrary numbers we assign based on our chosen rulers or clocks. Okay, so if C, H, and G are kind of definition dependent, what about something that is a ratio but still gets cited, like the ratio of electrons to protons?
Ah, yes. Non-Ph.D. You see proponents like Hugh Ross arguing this ratio has to be tuned precisely to 1-to-1.
Why? What happens if it's off?
The argument is that if it weren't exactly 1-to-1, the universe would have a net electric charge, and even a tiny imbalance, like one extra electron for every, say, 10,000 protons.
The electromagnetic force, which is vastly stronger than gravity, would just dominate everything.
Right, it would overwhelm gravity. You wouldn't get neutral atoms forming properly, let alone stable structures like galaxies or stars. The universe would just rip itself apart electrically.
Okay, that sounds like a pretty serious fine-tuning problem on the surface.
Mm-hmm.
A tiny imbalance has huge consequences.
It does sound like it. But the refutation here is incredibly direct. And it brings us right back to symmetry and Noether's theorem. Why must the ratio be exactly 1-to-1? Because the universe as a whole is electrically neutral. This perfect balance isn't tuned. It's required by a fundamental law to charge conservation.
And charge conservation comes from?
It stems directly from something called gauge invariance in electromagnetism. Basically, it's a symmetry requirement. The physics of electricity and magnetism has to be invariant. It has to look the same under certain kinds of mathematical transformations called local phase transformations.
So another symmetry principle demands a conservation law.
Exactly. Gauge invariance demands charge conservation. Charge conservation dictates that the total net charge of a closed system must remain constant. If the universe arose naturally, perhaps from a vacuum state which has zero net charge,
then the total charge of the universe must remain zero.
Correct. And for the total charge to be zero, the total positive charge from protons must exactly cancel the total negative charge from electrons. The number of electrons must equal the number of protons.
So no fine-tuning needed. It's a physical necessity baked into the structure of the standard model itself.
Precisely. It's required by the math that describes electromagnetism.
Okay, that clears up the arbitrary and the charge neutrality issues. Now let's move into the really big cosmological parameters, the ones dealing with the whole universe's fate and structure. These are where you see those truly astronomical probability numbers thrown around.
Right, the heavy hitters of the fine-tuning argument.
Let's start with the relationship between the universe's expansion rate and its mass density. There's that famous claim, often linked to Stephen Hawking, that if the expansion rate, say, 1 second after the Big Bang, had been just slightly smaller by just 1 part in 10 to the 17, the universe would have immediately recollapsed under its own gravity, gone back into a big crunch almost instantly.
Right. And if it had been slightly faster, it would have expanded too quickly for gravity to pull matter together to form galaxies and stars.
Yeah, that's the classic flatness problem formulation.
Yeah.
And it's a great example of how a kernel of truth can get twisted into something that sounds like a miracle. Because within the framework of classical general relativity without inflation, yes, the initial conditions do look incredibly fine-tuned to get the universe we see today, one that's very close to geometrically flat.
Yeah.
But that problem is basically solved by the best extension of the Big Bang model we have, inflationary cosmology.
Inflation. Okay, explain how that works. It happened super early, right?
Yeah.
Extremely early, around 1035 seconds after the Big Bang, according to the model. The idea is the universe went through this period of absolutely staggering exponential expansion. It grew superluminally faster than light doubling in size maybe 100 times or more in a fraction of a second.
Whoa. Okay, so how does that massive fast expansion fix the density or flatness problem?
Think about the geometry of space. Imagine the surface of a sphere, like a basketball. Before inflation, maybe the universe had significant curvature, like that basketball surface. Lots of wrinkles, variations in density.
Okay.
Now take that basketball and inflate it incredibly rapidly, maybe by a factor of $10 or much, much more, until it's the size of the entire observable universe we see today.
What happens to the curvature?
From the perspective of any small patch on that now enormous sphere, like our observable universe, the surface looks almost perfectly flat, just like the Earth looks flat to us locally, even though it's a sphere. Inflation stretches out any initial curvature so much that the universe inevitably becomes geometrically flat on large scales.
And flatness relates to density how?
Here's the key link. A universe that is geometrically flat must have an average mass energy density that is extremely close to a specific value called the critical density. This is the density required to perfectly balance the outward expansion and the inward pull of gravity over cosmic time.
So inflation doesn't just flatten the geometry, it automatically drives the density to the critical value.
Exactly. The incredible precision needed between the expansion rate and the density isn't some miracle that needed tuning. It's a natural physical consequence and actually a successful prediction of the inflationary model.
And inflation itself has observational evidence supporting it.
Oh, yes. Crucially, it explains the amazing uniformity we see in the cosmic microwave background radiation, the afterglow of the Big Bang. It solves several major problems with the older Big Bang model simultaneously.
Okay, that really undercuts the 1 in 10 to the 17th claim. Inflation makes the near critical density a natural outcome, not a fine-tuned coincidence. But we still have the really big one, the elephant in the room.
Cosmological constant, lambda.
Yeah, lambda, or the vacuum energy. This is the parameter they claim is tuned to something like 1 part in 10 to the 120. That number is just incomprehensible.
It is. And this 1020 discrepancy is probably the most dramatic example of how a calculation that is, frankly, simply wrong, as the source puts it, can lead people down a massive philosophical rabbit hole.
So what's wrong with a calculation that gives 10 to the 120?
The standard calculation, the one that generates this enormous number, tries to estimate the vacuum energy by summing up the quantum zero-point energies of all the fundamental particle fields. That's the minimum energy fields have even in empty space.
Okay.
The mistake is how they sum it. They basically add up these energy contributions for all possible modes up to a theoretical maximum energy scale called the Planck energy over the entire volume of the observable universe.
And that gives a huge number.
Colossal. About 120 orders of magnitude larger than the tiny non-zero vacuum energy, what we now call dark energy, that we actually observe driving the universe's accelerated expansion.
So if summing over the volume is wrong, what's the right way to think about it? Why is volume the wrong approach?
The correction comes from bringing gravity, specifically black hole physics, into the picture. We need to consider the holographic principle.
Holographic. Like a hologram.
Sort of. The principle, stemming from work by Bekenstein and Hawking on black hole thermodynamics, suggests that the maximum amount of information or entropy that can be contained within a region of space isn't proportional to its volume.
It's proportional to
Its surface area. Like the information needed to describe a 3D object could somehow be encoded on a 2D surface bounding it. The universe, in terms of its information capacity, seems to behave like the ultimate black hole.
Okay, so information scales with area, not volume. How does that fix the vacuum energy calculation?
If the total number of possible quantum states or degrees of freedom in the universe is limited by the area of its boundary, the cosmic horizon, not its volume, then you shouldn't be summing energy contributions over the volume. You should effectively be summing them in a way constrained by the surface area.
And when physicists do that, when they calculate the maximum possible vacuum energy density consistent with the holographic principle,
they find that the energy density is naturally constrained to be roughly equal to the critical density of the universe, which is exactly the small value we actually observe.
So just changing the fundamental assumption about how information scales from volume to area based on black hole physics makes that 120 orders of magnitude discrepancy basically disappear.
It essentially resolves it. It shows the naive volume calculation was the wrong way to combine quantum field theory and gravity. The alleged fine-tuning problem vanishes. The observed small value is actually close to the maximum value allowed by holographic bounds.
That's incredible. Are there other ideas too?
There are. Some approaches in relativistic quantum physics involve things called ghost fields, theoretical particles with negative energy. If the universe has a fundamental symmetry between positive and negative energy states, these could potentially lead to an exact cancellation, making the cosmological constant precisely zero.
So while we observe a small positive value now, dark energy, the idea that it had to be tuned down from some colossal value by 120 orders of magnitude is based on
a fundamentally flawed calculation that ignores crucial physics, particularly the interplay between quantum fields and gravity as understood through the holographic principle. That 10 number shouldn't be taken seriously as evidence for fine-tuning.
Okay, that tackles the big cosmological ones. Let's shift focus now, maybe down to the scale of stars and atoms. The parameters needed for chemistry, for elements like carbon that are essential for life as we know it.
Right. Moving into the nuclear and stellar realm, this brings us to probably the most famous story in the fine-tuning playbook, the Hoyle resonance.
Fred Hoyle, the astronomer. And this is about how carbon is made in stars.
Exactly. Inside aging stars, the main way carbon-12 is formed is by fusing 3 helium-4 nuclei together. This is called the triple alpha process. Hoyle realized this process seemed way too slow to produce the amount of carbon we see in the universe, which is obviously crucial for life.
So what did he predict?
Based on the need for more carbon, he predicted that the carbon-12 nucleus must have a specific, undiscovered, excited energy state, a resonance at almost exactly the combined energy of a beryllium-8 nucleus, which is unstable, and another helium-4 nucleus. This resonance would dramatically speed up the reaction.
And he was right. They found the resonance.
He was. They found an excited state at about 7.65 MeV, very close to where Hoyle predicted, around 7.7 MeV. And Hoyle himself later made comments suggesting this looked like the work of a super intellect monkeying with physics to make carbon possible.
That sounds like a slam dunk for fine-tuning. If that resonance was even slightly off, no carbon, no life.
That's the narrative. But the physics tells a more nuanced story. First, some historical analysis suggests Hoyle's original prediction wasn't primarily anthropic reasoning. It was based more on stellar nucleosynthesis calculations needing some way to make more carbon.
Okay, but what about the resonance itself? Is it really that finely tuned, that narrow a window?
Not really. While Hoyle's prediction was brilliant, subsequent, more detailed calculations show that sufficient carbon for life would actually be produced even if that resonance energy level varied over a pretty substantial range.
How substantial?
Roughly from near the ground state energy of carbon-12 up to about 7.933 meh. That's a much wider window than the knife edge often implied.
So it's not quite the miracle adjustment it's made out to be?
And furthermore, the existence of such a resonance isn't that surprising from a nuclear physics perspective. You're dealing with loosely bound systems of alpha particles, helium nuclei. These kinds of systems, where particles are sort of oscillating near the threshold of being bound, naturally tend to produce low-energy resonances.
It's just quantum mechanics doing its thing.
Pretty much. It reflects the natural behavior of nuclei governed by the strong force and quantum rules, rather than some incredibly precise, externally imposed balance just for carbon.
Okay. What about another nuclear parameter? The neutron-proton mass difference. That tiny difference seems critical.
It is definitely critical. The neutron is slightly heavier than the proton by about 1.29 MeV mega electron volts.
And why does that small difference matter so much?
Well, think about it. If the neutron were lighter than the proton, protons would decay into neutrons, and you'd basically only have neutrons and electrons. No stable hydrogen, no chemistry.
Man, disaster.
And if the neutron were too much heavier than the proton, say, by more than the binding energy of a neutron in deuterium, then neutrons inside nuclei would become unstable and complex nuclei couldn't form. Also, free neutrons need to decay into protons in the early universe to leave us with the hydrogen fuel for stars.
So it seems like there's a narrow window for that mass difference. The source mentioned maybe 10 MeVs wide.
Right, it has to be in a range that allows both stable protons and neutrons that can decay when free but be stable inside most nuclei. But again, we need to ask, is the actual value of 1.29 MeV somehow chosen or fine-tuned, or is it a natural consequence of deeper physics?
And the answer is?
We look to the Standard Model, specifically to the quarks inside protons and neutrons. A proton is 2 up quarks and 1 down quarks. A neutron is 1 up and 2 downs.
Okay.
Now, the strong nuclear force, which binds quarks together, treats up and down quarks almost identically. So based on the strong force alone, the proton and neutron masses should be very nearly equal.
So where does this small difference come from?
It comes from 2 main effects. One is the slight mass difference between the down quark and the up quark themselves. The down quark is a tiny bit heavier. The second is the electromagnetic effect. The 2 positively charged up quarks in the proton repel each other slightly, adding a bit to its mass energy.
And these effects are just natural consequences
of the electroweak interaction and how quarks get their mass from the Higgs field. Based on our understanding of quark masses and electromagnetism, the expected difference between the neutron and proton mass falls naturally within a range of, say, 1 to 4 MeV.
And the actual value is 1.29 MeV.
Exactly. It's comfortably within the range you'd expect just from the underlying physics of quarks and forces. It's not some bizarre value plucked out of thin air. It's a direct, calculated consequence of the standard model structure. No fine-tuning needed.
This leads us right into what seems like the biggest methodological weakness of the whole fine-tuning argument.
Right.
You mentioned it earlier, the way they often just vary one parameter at a time.
Yes, this is crucial. The source calls it a dubious and scientifically shoddy method, and that's not too strong. When a proponent says, if we change constant x by 1%, the universe becomes lifeless, they're almost always implicitly assuming that all other constants, y, z, etc., are held absolutely fixed at their current values.
Which isn't realistic.
It completely ignores the possibility of compensation. Maybe if constant x changes slightly, a small corresponding change in constant y could restore the conditions needed for life. The different parameters might be interconnected.
Can you give an example of that compensation?
Sure, let's stick with the neutron-proton mass difference. Suppose it were slightly larger, maybe making it harder for stable nuclei to form. Could that be compensated?
How?
Well, perhaps a slight change in the strength of the strong nuclear force could adjust nuclear binding energies to compensate. Or maybe a change in the electron mass could shift the balance in beta decay. The point is, the universe isn't necessarily balanced on a single knife edge. It might be more like a broad plateau where multiple variables can shift together while still allowing for complexity.
Have people actually studied this? Varied multiple parameters at once?
Yes, they have. Physicists like Robert Jaffe and his colleagues did work where they varied the fundamental quark masses simultaneously. They mapped out the island of congeniality, the regions in this multi-parameter space where basic conditions for complex chemistry, like stable nuclei, could still exist.
And what did they find? Was it a tiny island?
No, they found a surprisingly wide band of possibilities. For the neutron-proton mass difference, the viable range was much wider than proponents claimed, maybe 29 MeV wide in their study. And importantly, our actual universe, with its specific quark masses, lies comfortably within that band, not teetering right on the edge.
So the universe seems more robust, more resilient to parameter changes than the single variable arguments suggest.
Exactly. It suggests a physical robustness, not a delicate, brittle fine-tuning that requires miraculous precision. Life might be possible across a much wider range of fundamental parameters than usually assumed.
Okay, one more from this category. The strength of the weak nuclear force, often denoted alpha dollar. This governs things like radioactive decay. Hugh Ross claims this is tuned to give the right ratio of hydrogen to helium coming out of the Big Bang.
Right. The weak force controls the rate at which neutrons and protons could interconvert in the very hot, dense early universe. As the universe cooled, the rate slowed down, and eventually the ratio froze out.
And that ratio determined how much helium was made.
Pretty much. The leftover neutrons quickly combined with protons to form helium-4. The neutron-to-proton ratio at freeze-out, which was about 1 neutron for every 6 protons in our universe, directly sets the primordial helium abundance, about 25% by mass.
So Ross argues the weak force had to be just right to get that 16 ratio.
That's the claim. But again, how precise does it need to be? Does life absolutely require a 16 ratio and 25% helium? Probably not.
What range would still work?
For stars to form and eventually produce heavier elements, you mainly just need a universe that isn't all helium and has plenty of hydrogen fuel. Calculations suggest that a neutron-to-proton ratio anywhere from about 110 up to maybe 13 would likely still lead to a universe capable of forming stars and eventually life.
And that wider range for the NP ratio translates into?
A much wider acceptable range for the strength of the weak nuclear force. It doesn't seem to require the extreme precision claimed.
Plus, could other parameters compensate here too?
Absolutely. Some studies have even looked at scenarios where the weak force is effectively zero, meaning neutrons would be stable. Even then, by adjusting other parameters like the strong force strength or quark masses, you might still be able to get astrophysically interesting universes, perhaps ones that make heavy elements through different processes.
So the claim of specific, necessary fine-tuning for the weak force strength looks pretty shaky too.
Very shaky. Like the others, it seems to rely on ignoring the robustness that comes from considering multi-parameter variations.
Okay, so if the established physics models seem to explain away the most cited examples of fine-tuning, either as definitional artifacts, consequences of symmetry, outcomes of inflation, or features within a robust parameter space, where does that leave the deeper questions? Like, where did the universe come from in the first place? Does science have anything to say about the beginning?
This is where we often see the argument shift. If fine-tuning isn't convincing, proponents might fall back on the idea that the universe must have had a beginning, and beginnings require causes. This leads us to the Cullum cosmological argument.
Right. That's the one with the simple premises. Remind us.
Premise 1, everything that begins to exist has a cause. Premise 2, the universe began to exist. Conclusion, therefore, the universe has a cause which is then identified with God.
Seems logical on the surface. Let's tackle premise 1 first. Everything that begins has a cause. Is that actually true, scientifically speaking?
Well, it certainly seems true in our everyday classical experience. Chairs don't pop into existence without a chair maker. But modern physics, specifically quantum mechanics, really throws a wrench into that absolute statement.
How so?
Quantum events often occur spontaneously without any specific identifiable prior cause determining the exact outcome or timing. Think of radioactive decay. We know the probability that an atom will decay any given time, but we can't predict when a specific atom will decay or why it decays at that precise moment rather than another.
It just happened.
It just happens, governed by probabilistic laws. Same for things like quantum jumps an electron in an atom moving from one energy level to another, emitting a photon. It happens spontaneously. So to claim as a universal premise that everything that begins must have a distinct cause seems to ignore the fundamental indeterminacy we see at the quantum level.
Okay, so premise 1 might be weaker than it looks. What about premise 2? The universe began to exist. Isn't that what the Big Bang model tells us? A singularity, a starting point.
That was certainly the picture from classical general relativity, based largely on the singularity theorems developed by Hawking and Penrose in the 60s and 70s. If you run the expanding universe backwards in time using just GR, you inevitably hit a point of infinite density and temperature, a singularity which looks like a beginning of time itself.
But that's just using classical gravity, right? What happens when you add quantum mechanics?
That's the crucial step. Hawking himself, later in his career, argued that when you incorporate quantum effects, especially the uncertainty principle, near that very early, very dense state, the singularity gets smeared out. It disappears.
How does that work?
Quantum uncertainty prevents you from simultaneously knowing the exact position and momentum, or energy and time, on incredibly small scales. This inherent fuzziness prevents the universe from collapsing down to an infinitely small point with infinite density. The space-time cone doesn't reach a sharp tip at time zero.
So the universe might start with a finite, non-zero size, no infinite density singularity.
Exactly. The beginning might be more like a transition from some prior quantum state, rather than an absolute creation ex nihilo at a single point in time. The very concept of a beginning in the classical sense might dissolve when quantum gravity takes over.
If there's no singularity, no absolute start time, how could the universe have originated naturally? What's the mechanism?
A leading candidate mechanism is quantum tunneling.
Tunneling, like particles going through barriers they shouldn't be able to cross classically.
Precisely. We know quantum tunneling happens. It's essential for nuclear fusion inside the sun, for example. Protons tunnel through the electrostatic repulsion barrier to fuse. It's a real observed quantum process.
So how could the universe tunnel?
Well, physicists like Alex Vilenkin and others developed models showing how the entire universe could, in principle, tunnel into existence from a prior state. Perhaps from a state of nothing, which in physics usually means a quantum vacuum state, potentially with zero total energy.
It just spontaneously appears, like a quantum fluctuation.
Sort of, but on a cosmic scale. It's a mathematically described process within quantum cosmology that allows for the emergence of space-time and energy from a state without them, governed by quantum laws, without needing an external trigger or cause. It provides a plausible, natural mechanism for an uncreated origin.
Wow. Okay, so a natural origin seems physically plausible. And this idea, combined with inflation, leads pretty directly to the ultimate naturalistic answer to the fine-tuning puzzle, doesn't it? The multiverse.
It really does. If inflation happened, it's very difficult to see how it would happen just once. The mechanism that drives inflation, once started, tends to create new inflating regions, essentially, new universes, constantly. This is called eternal inflation.
And string theory suggests many possible universes, too.
Yes, string theory predicts a vast landscape of possible vacuum states, perhaps 10,500 or even more, each corresponding to a universe with potentially different physical constants and laws.
So combine eternal inflation with the string theory landscape, and you get...
A multiverse, an enormous ensemble of universes, possibly infinite, each with its own set of physical parameters, most likely determined randomly during its formation.
And how does that solve fine-tuning?
It solves it via the weak anthropic principle, the non-controversial one we started with. If there are countless universes out there with all sorts of different constants.
It's statistically inevitable that at least one of them, just by chance, will happen to have the combination of parameters that allows stars, galaxies, chemistry, and eventually life to form.
Exactly. And obviously we find ourselves living in that kind of universe because we couldn't exist in any of the others.
So the universe isn't fine-tuned for us.
We, or life in general, are fine-tuned through evolution to the specific conditions of the universe we happen to inhabit. The multiverse flips the perspective entirely.
But hang on, isn't the multiverse just unfalsifiable? How could we ever test it? Doesn't that make it philosophy, not science?
Yeah.
It sounds a bit like an escape hatch.
That's a very common and very fair criticism. And it's true, we currently have no way to directly observe other universes. However, the distinction is important. The multiverse isn't usually proposed as an ad hoc explanation for fine-tuning. Rather, it emerges as a natural, maybe even unavoidable, consequence of our best, most well-tested fundamental theories, inflation and string theory.
So if those underlying theories were proven wrong,
And the scientific motivation for the multiverse would largely evaporate. It's not unfalsifiable in principle, its support rests on the validity of the theories that predict it. Right now, it stands as the most parsimonious naturalistic explanation consistent with those theories, even if direct verification is beyond us.
okay, it shifts the perspective from why this universe to why not, given potentially infinite chances.
Precisely.
So let's circle back one last time to those incredible probability numbers, the 1 in 10 to the 10 to the 123, the 1 in 10 to the 120. If the multiverse offers one way out, are there other reasons why those numbers aren't scientifically compelling evidence for design?
Yes, absolutely. Simple probability arguments, on their own, are pretty weak when arguing for supernatural causes. Why? Because they usually only calculate the odds of the event happening naturally without giving any comparable probability for the supernatural alternative.
Like your coin flip example earlier.
Right. What's the probability of a fair coin lands heads 100 times in a row? Tiny. But does that prove a wizard did it? How do you calculate the probability of a wizard existing and deciding to influence the coin? You can't.
There's no baseline probability for the supernatural explanation.
Exactly. And more fundamentally, once an event has happened, like our universe existing with its specific properties, its probability is 100%. It happened. To argue for fine-tuning from probability, you'd need to rigorously show that the probability of natural processes producing such a universe is vastly lower than the probability of supernatural processes producing it. And you just can't assign a number to the latter.
But isn't there a more formal way to handle these conditional probabilities? You mentioned Bayesian analysis.
Yes, the Ike-to-Jeffries Bayesian analysis tackles this head-on. Bayesian probability is all about updating your belief in a hypothesis based on new evidence, they asked. If we start by considering two hypotheses, naturalism, N, the universe operates only by natural laws, and supernaturalism, S, a supernatural creator exists, how should learning that the universe is life-friendly, F, affect our belief in N versus S?
Okay, what do they find? Does discovering F support S?
Counterintuitively, no. Their analysis shows that finding the universe to be life-friendly, F, given that life exists, L, actually increases the relative probability of naturalism, N, compared to supernaturalism, S.
Wait, finding the universe is perfectly set up for life makes naturalism more likely? That sounds backwards.
It does at first glance, but think about it this way. What kind of universe would you expect under each hypothesis? Under naturalism, if life is going to exist, it can only exist if the natural laws and constants happen to fall within the narrow range that permits it. So finding F is expected if L and N are true.
Okay.
But under supernaturalism, assuming a powerful creator who wants life, L, that creator isn't bound by natural laws. They could presumably create and sustain life under any physical conditions, even conditions wildly hostile by natural standards. They wouldn't need the delicate fine-tuning.
I see. A god wouldn't need the constants to be just so. They could make life work anyway.
Exactly. An omnipotent being doesn't need to rely on this incredibly precise balancing act of physical constants. The fact that the universe does seem to require this precise balance according to natural law makes it look less like the work of an unconstrained supernatural agent and more like a natural outcome where life simply arose where the conditions allowed it.
So the very fine-tuning that proponents point to as evidence for God actually argues against that specific type of creator, according to this Bayesian analysis.
That's the fascinating conclusion. The more delicately tuned the universe appears to natural laws for life, the less likely it seems that it was created by a supernatural entity who wasn't bound by those laws in the first place. The creator performed an unnecessary, clumsy balancing act when they could have just made life work directly.
That really turns the whole argument on its head.
It does. It highlights the philosophical assumptions baked into the fine-tuning argument itself.
Okay, so wrapping this deep dive up, we've really gone through the major claims. We've seen constants fixed by definition, like C. We've seen ratios like electrons to protons fixed by fundamental symmetries and conservation laws like charge conservation.
Yep, gauge invariance.
We saw the big cosmological parameters like the density expansion rate and the cosmological constant explained naturally by inflation and by correcting the calculations using things like the holographic principle.
Right, fixing that $10 issue.
And the nuclear constants, like the Hoyle resonance or the neutron-proton mass difference, seem to fall within naturally expected ranges, especially when you allow for multiple parameters to vary and compensate for each other.
Showing robustness, not brittleness.
So, in synthesis, it really feels like the universe looks pretty much exactly as it should look if it were governed by objective, natural laws that demand symmetry and invariance. The parameters seem constrained by necessity or definition, not by design.
That's the conclusion the physics points towards. The fine-tuning fallacy seems to rest heavily on, 1, sometimes getting the physics wrong or using outdated models, and 2, making this arbitrary, narrow assumption about the parameter space, often by varying only one thing at a time.
And there's one last point. Maybe we should touch on the definition of life itself in these arguments.
Absolutely. Almost all fine-tuning arguments implicitly assume that life means life exactly like us. Carbon-based, water-solvent, DNA-using life, needing the specific elements made in stars like our sun, on a planet with liquid water, plate tectonics, a magnetic field, the whole checklist.
They rarely consider alternatives.
Very rarely. What about silicon-based life? Life using ammonia as a solvent? Life based on completely different information-carrying molecules? Life that could arise in radically different environments, maybe in subsurface oceans or even in interstellar dust clouds? The arguments assume a stunning lack of imagination about what life could be.
So they're fine-tuning for a very specific, maybe even parochial definition of life.
Exactly. Which brings us to maybe a final provocative thought for you, the listener, to mull over.
Okay.
If the underlying physics, driven by symmetry and invariance, is actually quite robust, allowing for complexity across a wider range of parameters than often claimed, and if complex systems, things that are nonlinear, interacting, dissipative, tend to self-organize naturally, then maybe the emergence of some form of complexity, some form of self-replication and information processing, which we might broadly call life, isn't the surprising part. Maybe it's a natural, perhaps even inevitable outcome of the universe's fundamental operating principles playing out over billions of years.
So the question isn't, why is the universe fine-tuned for our life?
Maybe the more interesting question is, given the apparent robustness of physics and the tendency towards self-organization, is it more surprising that some form of life exists, or is it more surprising that some people cling so tightly to a definition of life so narrow that it requires a miracle, when science increasingly suggests that complexity in life might just be what universes do?
That's definitely something to think about. The universe might be less fine-tuned and more generative.
Perhaps. The physics certainly doesn't seem to require the tuner.
This has been The Deep Dive.
Hey there, you arrived to the end of this episode. You can always check out my YouTube channel and also keep watching because there are 7 episodes. So if you enjoyed this one, hopefully you are going to enjoy the next one. I always like to remember that you can support my work by buying my books. Even though I still don't have a book about religion, which is the main topic of the podcast, I do have a book about artificial intelligence. And also I have a blog called Scientists Free from Religion on Medium. And there are several blog posts there. And you can enjoy it, you can read it, and you can subscribe to my YouTube channel, you can share it with your friends. So hopefully I can hear from you and hope you had an amazing time. So hope to see you in the next episode.